Okay, so welcome to this new lecture on machine learning. Uh, in this lecture, we will actually go with straight away. I will teach you something called supervised learning. Sorry, unsupervised learning, because I had already taken a course last year on machine learning where I talked in a greater depth about supervised learning. Due to interest of time, last year I couldn't actually cover unsupervised learning. I just taught you very basic about K-means and all that. These set of lectures are to look at unsupervised learning in depth. And as said in the previous class as well, we'll start from scratch. We'll start the entire unsupervised learning concepts from scratch. And what we do is we will actually also solve questions that are common to GATE DA exam. Now, GATE DA exam, the questions that we solve can also be from topics other than machine learning, which are there in your syllabus. So it will help you to also be thorough with, if we can, then we will solve the questions given in the today's class about topics that are other than machine learning. So without wasting any more time, let us start with the lecture. I'll cover about unsupervised learning. We'll cover K-means clustering. Let's quickly go to the syllabus, what is planned to cover in this class. Yeah, as you can see, the syllabus, the topics that are underlined are planned to be covered in this set of lectures. We start with unsupervised learning today, where I talk about something called clustering algorithms. What are clustering algorithms? And also we will discuss about unsupervised learning in general, what it is, how does it work. We'll discuss about K-means and also K-medoid algorithm. And then in the next class, we will go with hierarchical clustering. Then in the next class, we will look at dimensionality reduction and PCA. And in the last class, we will look at LDA, if we get time. So that's the 4 lectures that has been planned for ML this season. Let's start with unsupervised learning. Now, the basic funda that you have to kind of understand when it comes to unsupervised learning is, right, why do we call something as unsupervised learning? For people who know supervised learning, if you are given a data set D, right, the data set D may contain n points, each point being the set of features x1 and a label y. What does the label y mean? The label y could be a continuous variable, in which case, for example, if you want to predict the house prices, if you want to predict the temperature at a given time, you want to predict what is the money that the person has after some time. So y is nothing but could be either a regression problem where your y is a real number, or it may belong to some categories. For example, it may be like, do you actually if there is a details of a person, will he actually pay back the loan or not? Will you, so given the health details of a person, does the person have cancer or not? So in this case, your y belongs to some category C or some classes C. So this was supervised learning because you were given this y value for each data point, right? Y1, Y2, and so on and so forth. So this is your supervised learning. Okay. In this class, we are not focusing on supervised learning. There have been a lot of lectures that we have already covered. Please check out them in the playlist given. We will actually be covering about unsupervised learning. Now, in unsupervised learning, there is only one difference. You are not given the labels Y. You are only given data set X1, X2, X3, and so on and so forth. Okay. Now, here is the thing. to explain you why we need this type of data as well and what can we actually do with this data. Because if you see, supervised learning is kind of driven by the variable y, right? So why do we actually need unsupervised learning? To explain you this, let's take a simple example. So for example, let's say, so all of you here might have heard about the Domino's pizza place, right? Domino's is one of the common places where you can buy pizza from. And let's say Domino's has two variants of pizza, right? All of you might love something called cheese burst pizza, and you might love also something called hand tossed, right? There's just names that they have given. So there's something called cheese burst, there's something called hand tossed. Okay. Now let's say Domino's, you are the person who has been given to increase the sales of Domino's. You are the sales manager. You want to run an ad campaign. Okay. Now the idea is that you are not getting the response from people that you are supposed to get. So Domino's, you have been tasked that you have to increase the sales. And by increasing the sales, you want to make sure that you will be able to give discounts on a particular category of pizza. Okay. Now, which category do you want to select? Do you want to select cheese burst or do you want to select hand tossed? Now, what you did was you collected this historical data of the people who bought cheese burst and hand tossed pizza. Okay. Let's say what happened was, what you did was in a graph, let's say you try to plot the people who ate hand toast, and let's say the people who ate hand toast is this. Okay, and let's say the people who ate cheese burst are this. Okay, okay. So now if I ask you which is more, if you see cheese burst pizza, people ate more, right? So if you want to run discounts, you know from this data that cheese burst pizzas are ate more. So what you will do is you will create an ad campaign for cheese burst pizzas. So you give the discount to those people on cheese burst pizzas so that you will get more and more customers. Now, this would have been a supervised learning problem because what I'm saying is given a person X1, you can say Y could be either cheese burst or hand tossed. Right? So this still looks like a what shall I say? This still looks like a supervised learning problem, and you are correct because here you are trying to say, given a data point X, whether that Y ate either a cheese burst pizza or sorry, either a cheese burst pizza or a hand tossed pizza. Now the thing is, given this data also, right? Let's say you put this Y also in the set of features. Okay. And what you try to do was you try to segregate this data depending on regions. Okay. For example, an X would be like given a place. For example, let's say for me, I stay in Bangalore. So in Bangalore, there are multiple places. Okay. In Bangalore, there are multiple places. Let's say we have Whitefield. Let's say we have HSR, and so on and so forth, right? We have different places, and these are kind of captured in your set of features. Okay. Now what you can do is you can make sure that, let's say you have this data here, you plot the region like this and the set of people X. Okay, let's say this is Whitefield, this is HSR, this is Koramangala, and so on and so forth. Let's say your people who ate from Whitefield are like this, about like 5 people. Okay. Let's say from HSR, it's about um, 8, or say, let's say this many people, right? 8 people. From Koramangala, let's say they are much more. They are much more. Now, next time if Domino's wants to run an ad, they want to make sure maybe that people from Whitefield don't know about Domino's Pizza, or they don't know the nearest outlet, or maybe the Domino's Whitefield outlet might not be selling as expected. They can cluster this data in these 3 clusters, and they can report that people who eat pizza from Koramangala are happy. People who eat pizza from HSR, we can run some campaigns. People from Whitefield, we have to put more advertisement so that they know that there is a Domino's Pizza. Maybe we can also run an ad campaign so that more people from Whitefield start eating Domino's Pizza. So this way, given the data set D, you partitioned this data set into 3 data sets. One is called Whitefield, one is called HSR, one is called Koramangala. The same data set, right? You just took a feature and you segregated the data set into 3 different sets. This is nothing but clustering. Now, by doing this, what did you get? You have more decisions that you can take. For example, just what I said. Whitefield, when you segregate, you can make sure that people from Whitefield, you will run ad campaign. HSR, people you may want to run discounts. Koramangala, everything is okay. So you will maybe want to I don't know, maybe you will not focus on it. You'll say that, okay, Koramangala is fine, right? Why should I focus on it? Right? So this way, to get more insights on the features of the data, we kind of use unsupervised learning. Similarly, if I give you the set of features, you kind of segregated them on the feature of what type of pizza people are having. People are having cheese burst more. So that kind of also gives you the fact that you will run ad campaigns, discount coupons on cheese burst pizza more than hand tossed pizzas. There are many examples of unsupervised learning as well. Google every day does unsupervised learning. So if you know, there is something called Google News, right? It has news of everyday category. If you just go to Google News, right? They don't actually manually do this. For example, if there is a news on politics, someone doesn't manually go and puts it into the category of politics. No. Okay. There's actually clustering algorithms which kind of look at the data, look at the news, and segregates and tries to find out that boss. This article is on politics, so I will put it in the category of politics. For example, if tomorrow there is a article on Virat Kohli, now, Virat Kohli typically is associated with something called cricket. So, it will go into the category of sports. So, the different news articles that are there, Google has already partitioned it into different clusters. And depending on the news article, that particular news article goes into the particular category. Okay, so this is one of the real life examples that are there by Google. There are other examples as well. There are many examples in a sense, but these two, if you remember, they are enough for your exam. I mean, you get the point, right? I mean, how you need to find out insights from the data. Okay, so this is about brief about unsupervised learning. Now, unsupervised learning are typically there is a process called clustering involved. Clustering means given a set of data points, can you cluster them into different categories? For example, clustering in your syllabus, there are many more algorithms, but I'm only focusing on what is there in your syllabus. Clustering is divided into something called partition-based clustering and hierarchical clustering. Okay, hierarchical clustering. Now, partition-based clustering is divided into another two parts. One is called K-means, another is called K-medoid. And hierarchical clustering, we'll look into it later. Today we are focusing on partition, that's why I'm writing that. Hierarchical clustering is further divided into something called single linkage, complete linkage, and average linkage. We'll go to that later in the next class, okay? For today, we'll focus on partition-based clustering algorithms. Starting with the first one, which is K-means clustering algorithm. Okay, now it's a very, very simple algorithm. Okay, I'll explain it by an example. You will actually write the algorithm if I explain you, right? It's that easy. Okay, so see. So we are trying to find the clusters. Okay, we are trying to find the we are trying to cluster the data point. First of all, in a partition-based algorithm, okay, in a partition-based algorithm, what you do is you partition the data set into k distinct subsets. Okay, and let's say I call this partition of the data set D. So you get k different subsets. I just call them A1, A2, so on and so forth till AK. So now you understand what is a K in K means, right? K in K means and K-medoids means how much clusters you want to have. Now they should all follow the rules of partition, which means each of these subsets AI should not be equal to 5. It should not be an empty set. Any two subsets AI and AJ should have nothing in common. And third one, the union of all the sets AI should give you the data set D. This is a concept that you might have learned in GATE. For GATE CS people, you might have learned in discrete math what is a partition of a set. So it should be non-empty. Any two sets should be not have any common element, and the union of all the partitions should give you the data set D itself. Now, if you can do this, this is called partition-based algorithm. There is another one called hierarchical. We'll go to that later. You don't have to worry for now. Now, one of the most common partition-based algorithm is called K-means. Okay, and it is such a simple algorithm that you will actually laugh saying why when I'm teaching it, but again, it's there, so it's there. So let's take a data set and I will explain you what is K-means algorithm. Okay, I'll write the step by step and we'll also do it on the data set now. Okay, this way you will learn better. So let's say there is a data set of data points like this. This, and let's say this. Okay, these are two data sets. This is the data points you have. Kinda, you should have made all of them as crosses or circles because that way you kinda think it's a supervised learning problem. So I'll just make it like this. Okay. 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 Now, for a partition-based algorithm, the first step that you have to do is you have to decide the number of clusters you want. Decide the number of clusters, that is your K. you want. And now this number of clusters that you have, you may tell me now that, boss, how can I know that? If I know it, then why am I doing machine learning? No. So the point is, if you can tell me the number of clusters you want, I can give you a partition. Basically, the entire part about clustering is to partition the data set into K cluster. I'll give you a partition, I'll give you those AIs that obviously have to minimize a criteria. Again, what is that minimization? We'll look into it. Don't worry, just hold on. Now, there are also methods by which you can pick the optimal number of clusters. We'll look into that later, but there are methods that actually do that. So you decide the number of clusters you want, the first step. For example, in the above case, I just take the value of K as 2. Okay, you can take some Pandit has come and told me, boss, take K as 2, you'll get a good clustering output. So I took K as 2. Okay. Okay. Now the second step is, okay, you have to initialize the K centroids randomly. It might sound, what am I saying? But it's actually very simple. Just hold on. Initialize the K centroids randomly. And to differentiate the centroid, so centroid is basically, if you have a cluster, let's say, if you have a cluster like this, the red one, I may say that the centroid is a central point of the cluster, which is this. Okay, it's just a point. Okay. Now, since you put K as 2, in this case, if you see K is 3 actually, so this data set has 3 centroids. This data set has 3 centroids. So if you have selected K as 2, you can initialize the K centroids randomly. And to differentiate them, I just use the color orange to show you that it's a centroid. So let's say I take, I don't know, I take this as a centroid. Okay. This is, let's say, my C1. And maybe I take this as a centroid. Just random some point. Any point I could take, right? Some random point I took, C1, C2 as the 2 centroids. Okay. Now, these 2 steps should be clear by now. It's very simple. Now, let's go to the next step. The next step is, okay, next step is, for each data point, for each data point xi, okay, for each data point xi, compute the distance to each cluster centroid. Okay. Okay. The second step is classify xi, or classify would be something supervised terminology. So assign would be the right word. Assign xi to cluster with closest centroid. Okay, what do I mean by that? See. Okay, now focus on the data set. Okay, you have 2 centroids. Now what you do is you take each, I just reduce the sum of the points, okay, so that it doesn't look very ugly. So it actually doesn't add much aesthetic flavor if I put many points, because the point won't be very clear. So I just reduce the number of points in my data set. Okay, not much changes I've done, just reduce some points. You'll understand why I did. Now what you do is For each data point, for example, take this data point, right? You compute its distance from C2, you compute its distance from C1. Then you take this, you compute its distance from C1, compute its distance from C2. Take this, compute its distance from C2, compute its distance from C1. Compute this distance from C1, compute this distance from C2. Okay. Similarly, you compute this distance from C1, compute its distance from C2. Compute its distance from C2, compute its distance from C1. C1, C2, C1, C2. For each point, you compute the distance to each cluster centroid. That's the first. Okay. Now, let's emphasize on the first step. Okay. The first step now is, right? Now, the point is, I am telling you to calculate the distance of a point xi from a cluster centroid Cj. So for people who have learnt maths, they must have known that how do you calculate the distance between 2 points, right? There are different algorithms that exist. You might have heard of something called Euclidean norm. Correct, that's the same we will be using. So there are some distance measures, ways by which you can measure the distance between 2 points. Okay, the first one is called Manhattan distance. Okay, these are just terminology. You all have studied it, I guess, earlier. Okay, so the Manhattan distance between 2 points x, y is the summation of I equal to 1 to d, oh sorry, d confusing, to n, the absolute value of xi minus yi, where what is your n? N is the number of dimensions in your data set. So for in this case, if your value of n is 2, right, you have two features. If you see, you have put your points in a plane x comma x, let's say this is x1, this is x2, so you have put it in a 2 plane. For n is equal to 2, the distance between 2 points x comma y is, you just substitute the value of n as 2, you get x1 minus y1 plus x2 minus y2. Okay, so this just you might have studied this already in your class 10, 11, 12, I guess, distance formula. Now the other one which you might have learned is called Euclidean distance. Few people call it L2 norm, that's fine. So Euclidean distance. The Euclidean distance formula d between 2 points x and y is summation of I equal to 1 to n, right? xi minus yi whole to the power p. Okay, this is also controlled by a parameter p, and then you take this entire thing to the power 1 by p. Okay, now if this looks might complicated, but again, if you put the value of p as 2 and the dimension also as 2, which is the capital small n as 2, if you try to calculate the distance between 2 point x and y, you see, you definitely would have seen the formula. So if you just substitute here x1 minus y1 whole square plus x2 minus y2 whole square and to the power 1 by 2, so which is root over. This is the distance formula that you have studied in your class 11, 12. You can use any of these two distances. Which distance you should use when? You should know that. It's a very common interview question for any data science job. Typically, to answer this question, I want you guys to think a bit. Okay, take some time, pause this video, try to think the answer, and then we'll go into it. The hint that I can give you here is See, let's say there is a point like this. I'm just taking a random example. Let's say it's 1, 2. This is, let's say, 11, 2. Okay. Now, let's say this one is point P1. This one is point P2. Let's say there is a point here P3. This is, let's say, 4, 3. Okay. Now you want to calculate the distance between P1 and P3 and P1 and P2. If you use the Manhattan distance, so let's say it's P1, P2, P3. Let's say you use the Euclidean distance, P1, P2, P3. If you use the Manhattan distance, you get 10 point as 10, 11 minus 1 plus 2 minus 2. And for P3, you will get 4 minus 1 plus 3 minus 2, which is 4. If you take the Euclidean distance, it will be 100, right? 10 square. 10 square, and then you take the root, so it will be 10. And then you take 4 minus 1, 3 plus 1 plus 1, 2, so root 2. Okay. Now with this, if you see the nature of the output, right? If you see the nature of the output, you will be able to, I think I did some mistake, sorry, root 10, right? Not 4, root 10. So if you see the nature of the output, you should be able to answer, but still try this out and let me know the answer before the next class. I don't want to tell now because I want you guys to think. Just try to think if you want to penalize some errors more, some distances more, or something. Like I already told you the answer, but still think, okay? Anyways. Now let's come back to the algorithm. I assign, now I've done the computing the distance of centroid to each cluster centroid, as you compute the distance to each cluster centroid. Now you need to do something called, now you need to assign each data point to the nearest cluster, right? So again, for let's say, let me do one thing, okay? Let me take the second centroid, I'll color it with purple, okay? Now look at this data point here, okay? The one I am crossing, right? Which cluster should it belong to? The distance to C2 is more or to C1 is more? The distance to C1 is more. So this cluster will be classified as C2. Similarly, these points will be classified as C2. Now this point looks more closer to C1, so I'll cheat a bit. My idea was to, maybe I'll place it here. Sorry about that. So I'll put the cluster point there. And then the other cluster, and since I'm coloring it with orange, it will be this one. Okay, I assign the points to the nearest cluster that is there. Okay, this is the steps that I have written and I have executed it. Now there's one more step that will be there, which is to recompute the cluster centroids. So sorry, recompute the cluster centroids. So if you recompute them, this cluster centroids will send. And how do you recompute? So the point Ci will be nothing but the mean of all the points xj belonging to the cluster Ci. Okay, so if you want to compute, let's say C1 again, you will take the mean of all the points that belong to cluster C1, and whatever that comes, you'll get that as answer. For example, I think just doing a rough calculation, it will come here. So C1 will come here. Similarly, for C2, it will come here, I mean somewhere here. Okay, somewhere. Okay, it will come somewhere here. Now you repeat this process, you repeat these steps until and unless there is some fixed number of iterations that are there, or your cluster centroid's value does not change. Okay. Now, if you get this, then this is one of your cluster. This is here. another cluster. So at the end of the day, you get two clusters, and these two clusters, given the centroids that are there, you will be able to partition the data set into k different clusters. Okay, any questions? No? Okay. Now, let me give you one more example, and then maybe I'll ask you, I'll erase this part. Okay. So I'll just ask you one more small question here. Okay. So if I, now let's take a one-dimensional space. Okay. Let's say you have points like this. So you have some points like this. Okay. And you have some points like this. Okay. I give you two different clusters. Let's say this is one cluster and this is the other cluster. Okay. Let's say the same data set I will take again. And let's say I have points like this. Same points I have. Okay. And the second option of clustering would be, let's say this. I take this as one cluster and this as one cluster and this as another cluster. Can you tell me which is a better cluster? Just by looking at it. Or can I say that some cluster is better? If you see, technically the thing should have happened was these 2 points, right? This one and this one should have belonged to the right cluster if you want to do two-class clustering. Typically that should have been expected, right? That should have been expected. If you take 3 clusters, they look more clustered. They're better clustered, right? You can see this clear separation that is there. So now we are talking about a cluster being better or worse, right? We are talking about a cluster being better or worse. And can we quantify this? Can we say that this cluster is better, this is not better, this one is better, this one is not that well separated, this one has more cohesion, this one has less cohesion. Okay, let's not go to technical much. So what is a better cluster? Can we quantify it somehow? Turns out we can. So there are two metrics that exist. One just quantifies the cohesion, right? The cohesion that is there. The first one is called within cluster sum of squares. Within cluster sum of squares, this metric, what it does is it calculates for each data point I belonging to 1 to n, the distance of I, xi, that point, with the cluster that has been assigned to xi squared. So within cluster sum of squares. For example, if you have these two clusters, let's say the centroids are here, here, and here. For this one, let's say the centroid is here, and it is here. Okay. If you see the within cluster sum of squares difference for the below cluster, it will certainly be less than the one on the top. Okay, I hope you guys can see that. The within cluster sum of squares distance will be less for the below cluster because the distance of this point from the centroid versus only this point and this point from the centroid is lesser, has become less, right? So that's why the within cluster sum of squares should be minimum. And K-means algorithm tries to minimize this quantity only. It tries to minimize the within cluster sum of squares distance. This is one metric. And depending on this metric only, you can find out the optimal number of clusters. Now to find the optimal number of clusters, there is a method called the elbow method. What does the elbow method do? The elbow method, for different values of k, okay, this is the different values of k that is there. In your y-axis, you calculate the within cluster sum of squares value. And if you see for k equal to 1, the value will be maximum. And as you go more and more, k equal to 2 and so, depending on the data set, but typically the pattern that is formed is this. If you see, it looks like an elbow. That's why it's called elbow method. Now, if you see, right, let's say this point here for k equal to 2 is the point which is, because as you increase the number of clusters, you have to do more computation. It will increase your computational cost. So you would want to make sure that you don't want to go here because you would maybe overfit the model there. That is something you're not expecting to do. For example, if I give you the most optimal cluster, given a set of n data points, let's say there are points like this, right? If I make each point a cluster, so let's say each point is a cluster, right? So each point is a cluster. What do you think the within cluster sum of square will be? It will be 0, right? Because each cluster means, each point being a cluster means the centroid is also the same point. The distance between centroid and that point is 0. If you take the sum of them, it will be 0. So if you increase the value of k, but is this the right way to do clustering? No, right? What will you get by doing this, right? So you won't get much insight. So this is overfitting the model. This is a perfect example of overfitting. So you'd want to maybe stop at this junction when it starts to flatten out, in this case for k equal to 2, and that's when you can say that, boss, I found my optimal number of clusters. Okay, is it clear, everyone, starting from the top till here? Okay, okay, okay. This is about k-means algorithm. But as I said, there are two ways to quantify the goodness of a cluster. One is a within cluster sum of squares. We people also called it inertia. It's just a name. Okay, don't worry. So a few people also call it inertia. You can call it anything you want. So within cluster sum of squares is this. There is another metric called the Salient score. Well, there are some more as well, but these are there in your syllabus. So these two are there. So Salient score. Now Salient score is also simple. Let me explain it through an example. Let's say there are two clusters. This is one cluster. Let's say there is another cluster. Okay, you have found the cluster, best optimal cluster using elbow method. You have found the best cluster. Okay, and this is what you get. Okay, now this is C1, this is C2. Okay, two clusters you have. Now, in clustering, typically there are two things involved. One is called separation between the clusters. And if I ask you for a good clustering algorithm, take this example, okay? So we see this picture properly and answer. For a good clustering algorithm, Do you want the separation between the clusters to be maximum or the minimum? Correct. You want the separation between the clusters to be maximum. That's what you called a good cluster, right? Okay. So that is separation. Separation you want maximum. And there is another term called cohesion. Cohesion meaning points within a cluster, you may want to minimize that. And that's what within cluster sum of squares is, right? You try to minimize it. So a cluster can typically have these two properties. One is cohesion, one is separation. You would want the clusters to be as close as possible in minimizing the within cluster distance, cohesion, or you want the separation, and also you want the separation, which is the distance between two clusters, to be the maximum. Silhouette's code tries to measure both cohesion and separation. Okay, if you see within cluster sum of square, it doesn't kind of measure separation, but Silhouette score measures the same. Silhouette score, the value has the range from -1 to +1. I will not tell you now which value is better. We'll look at when we learn, we'll do that. Okay. Now to do Silhouette score, you select any data point. Okay. Let's take this data point. I select this data point xi. Okay. I select this data point. And now what I do is I calculate something called the cohesion score. I call it AI. It's just a name, AI. Okay, can name anything you want. It measures the cohesion. And how do you measure the cohesion? It's the same formula that you apply above. Instead, how do I measure it is, uh, it's the mean distance from all other points in the same cluster. In CI, the same cluster. Okay, so what is A of I? It is the summation 1 by n j equal to 1 to m, right? The distance of the point xi with the point xj. It's a mean. Okay. This is cohesion. And also you measure something called separation. Now separation is kind of denoted by this B of I. Separation is the mean distance from all points in nearby cluster. So whichever cluster is the nearest to CI, you take the mean distance from all the points in the nearby cluster. Now, since there are only two clusters here, so for this cluster C1, the nearest cluster is C2, right? So you take the distance of xi to all the points in C2. That is your separation. And so B of I 1 by m summation of j equal to 1 to m, the distance of xi to xj, where your xj belongs to cluster j, is the nearest cluster to xci. Okay, nearest to ci. So you calculated the separation, you calculated the cohesion. Okay. Now with this, the Silhouette score S is given by the formula B of I minus A of I, and you normalize it by writing it as the maximum of B of I, A of I. This is just to normalize and make it between -1 and +1. Now, as I said, I didn't tell you which is better, right? -1 or +1, which is better. Okay. Let's take some examples. Let's say you try to find out that there is some cluster where the A of I came out to be 0.1. The cohesion score that you get, value that you got is 0.1. Let's say you got B of I as 0.9. The distance between two clusters you get as 0.9. Now, as I explained you that B of I should be more because the separation should be more, cohesion should be lesser, that will be beneficial. So if you try to calculate the Silhouette score, what do you get? You get, sorry, I will write it here. The Silhouette score you get is 0.9 minus 0.1 divided by 0.9, which is about 8 by 9. Okay. Let's say if it were the other way around. Okay. Your Silhouette score will be minus 8 by 9. Okay. Now tell me which is the better one. As I told you, the cohesion should be minimum. This is the better one. So +1 means good cluster, right? More it is towards +1, it's better. More it is towards -1, it is bad cluster. Okay, Silhouette score is clear. Okay. So what did we cover so far? So we said what is clustering. We looked at the different distance metrics that are there. We looked at one partition-based algorithm, K-means. And we kind of took an example and tried to do K-means algorithm for the same. And then we looked at a way to minimize, to go with or find the number of clusters K, which is by using the elbow method. To use the elbow method, you need to know something called within cluster sum of squares, or also called inertia. And once you do that, then we learned that about Silhouette score, which is a way to find the quality of a cluster. And then we looked at the interpretation. How do you interpret a Silhouette score? The lower the value, the worse. The higher the value, the better. Okay. Any questions? No? Okay. Now there is a slightly different algorithm called K-medoid algorithm. Now first let me tell you why K-medoid was motivated. There are two reasons why K-medoid algorithm is also present along with K-means. There is some small kind of minute issues with K-means because of which I use K-medoid. Number one, these centroids, for example, let's say if I have only 2 points, right? I have only 2 points, this and this. Okay, let's say maybe these are 2 points. Okay, if you see, the centroid is actually neither this point nor this point. It is somewhere in the middle. So if you want to interpret the centroid, you cannot. Like it's not even a point that is there in the data set. The centroid, right? The centroid is not even a point in the data set. So what will you do with it? So this is called problem. There's a problem in interpretation of the centroid. If that would have been one of the points, then I also could have said that, boss, this point is the middle, the central point. So why don't you This is the central point. So this is the average, right? You could do more interpretation if it would have been a point. Now, just giving this as a centroid, it's not even a point. So in the data set, so what will you do with it? The second problem comes because you are using averages. So it is sensitive to outlier. Sensitive to outlier. Okay, whenever you take mean, please randomly you can say it's sensitive to outliers. Because you're taking the mean of the point to calculate the new centroid, right? And it's a very common statistic question. How is mean more sensitive to outlier? So that's why you use something called median, right? Median is not sensitive to outlier. Now K-medoid algorithm minimizes both of these two, eliminates both of these two problems at the cost of more competitive computation. So how does this algorithm work? The first step is simple. You select k random data points. So actual data points you select this time. You can't just randomly pinpoint anywhere. Select k random data points as your initial medoids. The second point, you select k random data points as your initial medoids. Assign each non-medoid data point. So each non-medoid data point that you have to the nearest medoid. You assign each non-medoid data point to the nearest medoid. The third step that you select is you calculate the total cost okay, which is the sum of distances and that's where things change, guys. So please pay attention. So you calculate the total cost, which is the sum of distances of each data point with the nearest medoid. Okay, so far so good. Nothing very difficult, right? So far so good. Let's call this TD. Let's call this TD. Okay. The fourth step, for each medoid M and non-medoid data point O, okay, for each medoid M and non-medoid data point O, first step is to swap M and O. You swap the point M and O. You calculate, after you swap M and O, your total cost will change. So you recalculate number 3, the total cost of each data point with the nearest medoid. Let's call this TD dash. Now you have swapped this M and O. Your expectation should be if the distance is less than TD, right? If the distance reduces, if the cost reduces, then you keep the swap, or you undo it. I mean, you did something wrong. It increased the cost, so you better don't consider that point as one of the points to swap. So you undo it. So this way your algorithm will work till you have number of iterations, or you actually um, don't find any change in the medoid. So this is called K-medoid clustering. It's very similar to K-means, just some small here and there, which is here we are talking in terms of actual data points. Okay. Okay. So last thing before I finish this partition-based clustering is the difference between K-means and K-medoids. Okay. K-means uses centroids, which means it uses mean. K-medoid uses medoids, which means actual data points. Okay. Second thing, K-means is sensitive to outliers. K-medoid is robust to outliers. Third point, K means typically there is no hard and fast rule, but typically it works well with Euclidean distances. While K-medoid, you can use any. Fourth point, or let me write, use any distance metric. Fourth point, K-means is faster and efficient. The entire problem occurs in the place where you do swapping. So if you have a large data set, performing this step will be a pain. It will be a pain. It will be very difficult to swap each data point with each medoid and then recompute and then try to find out. So that's the memory, the computational cost that you play. This lower. The fifth one is it is less likely to find global optimum, which is the best clustering possible, while K-medoid is more likely to find global optimum. Okay. If you guys have any questions, I will wait for a minute. If you have any questions, feel free to ask, put down in the chat before I move to the questions. The questions are planned. There are 6 questions. First, based on the topic that is taught today, three questions, simple questions only, not very difficult. And then we have some questions that are part of your GATE DA syllabus. Yes, any questions? Okay. Okay, I'll quickly go to the questions. Okay, seem to have a lot of theory slides just to be sure that you don't fall short. Okay, just taking some time to go to the questions. Yeah. Okay, so I hope you guys can see the first question. Which clustering algorithm is a simple one? Which of them uses centroids to represent the clusters? K-means, yeah, K-means. So K-means uses centroids um, uh, to represent clusters. In K-medoids, what represents the center of a cluster? Is it the mean of all data points? Is it the median of all data points? Is it actual data point? Or is it a randomly generated data point? It is an actual data point. Good. Which algorithm is more robust to outliers? Is it K-means, K-medoid, both are equally, or neither is robust? That's what if you learn the difference, K-medoid is more susceptible to outliers. Okay. Simple. Using Manhattan distance, can you find out the distance between the point 3, 4 and 7, 2? Simple problem.
You are currently the only person in this conference.
Okay. So using Manhattan distance, what is the distance between the points this and this? So Manhattan distance, if you remember the formula, one second, my iPad got disconnected for some reason. Okay, yeah, I'm back. So the distance between these points, let's call it P1, P2 is 7 minus 3 plus 2 minus 4, which is 6. Okay, we just take the absolute difference between each individual dimension. In k-means clustering, if the current centroids are given as 3, 3 and 7, 7, and there is a point 5, 5 equidistant from both, what would be this distance using Euclidean distance? It's typically just trying to find out the Euclidean distance between the points 5, 5 and 7, 7. So let's call it P1, P2. This is my P1, this is my P2. It's root over 7 minus 5 whole square plus 7 minus 5 whole square. This is nothing but root over 4 plus 4 root over 8, which is 2 root 2. Okay, try this out. I'll give you some time. Yeah. So certainly it's not C and D. You can actually be able to get the cluster. So you have to calculate the distance between 2, 3 and 5, 7, 7, 2 and 5, 7. Whichever comes closer, you will get that as an answer. All right. So what do you think? I think it should be 7,2. It looks more closer to that. You may also do the calculation. You will get the answer as 7,2. Okay. So these were all the questions that I had to cover for today's lecture. Whereas there is one question that was asked in GATE. We'll do that in the next class. And now what we'll do is for the other topics that are there in your GATE DA, this the class, as I said, will be a comprehensive class. Few I will teach for some time, and then we'll look at some GATE questions that are present in the previous year questions, previous year GATE, on other subjects that are also there in your GATE DA, so that you get a comprehensive kind of crash course for your entire DA exam. The ML lecture is over, so if you want to exit, you can exit. If you want to stay and practice, feel free to do that. So let's go to the questions for one by one. I'll give you some time to solve these questions. These questions I actually bought from, they are bought from, this should be question 1, then why question 2. These questions are from the mock exam that has been published by GATE in their website, GATE 2025 mock exam that has been published. So this is the first question. Please try this out. I think we did this in the class for people who have seen my discrete databases lecture, but for those who don't, maybe it's a new time to solve for you, and maybe try this out and we'll discuss the solution. Okay, any answer? So typically this rectangle is called entity and these diamonds are called relationship. For example, if a student registers for a course, then the entity course and the entity student are related by something called registration. Okay, that's how you read. So every two entities, if they are connected, they must be connected by a relationship. Okay, so instructor teach courses. Instructor teaches courses. Instructor teaches courses. Instructor teaches courses. Instructor teaches courses. All four options have the first one modern. This is an ER diagram. All the four options have it. Students registers for courses. Now, if you look at the first one, student is an entity. Here it is given as a relationship. So this is not correct. If you look at option B, this does not have any student, so it's already gone. If you look at option C, student registers for courses is there. If you look at option D, student registers for courses is there. Courses are allocated classrooms. Now there is a problem here in the third option. Courses are allocated classrooms, so the relation should be like this. But you are connecting two entities directly without any relationship in between, which is not allowed. So option 3 is also gone. Courses are allocated classrooms. Instructors guide students. So option D is the right answer. Okay. Okay. Let's say this is an array. It is heapified. Which one of the following options represent the first three elements of the heapified array? This is a question from data structures and algorithms, which is one of the most important topics for your exam. Yes. So typically you would want to make, if you heapify it, again, they are not given which min heap or max heap. Let's take a max heap. So the maximum element will come in the first element, will be the maximum element, which is 131. So 131, or either this or fourth will be the answer. The second element will be actually, sorry, so 131 is a maximum element. The second element will be the child of the root, in this case 131, 111, and then 90. So option D is the right answer. If you try to apply the heapify algorithm, you will get this as the answer. Okay. Okay. Let's see if you can answer this question in about 30 seconds. What is the product of all eigenvalues of this matrix? Are you guys calculating the eigenvalues and then doing it? It's gonna take a lot of time if you do that. You have that much time, sure. Okay, so you need to know the property that the product of all eigenvalues is the determinant of the matrix. Is nothing but the determinant of the matrix M. Now, what is the determinant of M? It is 1 times 9 minus 5 plus, sorry, 9 into 5 is 45, 45 minus 48, minus 2, 36 minus 42, plus 3, 32 minus 35, which is minus 3 plus 12 minus 9. 0. Option 3 is the right answer. Okay. Last question for today is this. So given in GATE 2024, they have added in the mock exam of GATE 2025. Please try this out. So C program, you have to tell me the output of the given program. Okay. So the answer is option B. Okay. So the input is given as the string 1, 2, 3, 4 and the new line character. This is the input. Right? GetChar will take one of these as input. So you calculate, you run the function f of x. Okay. Initially, your value of a is 1. So you call the function again, f of x. And later on, you have to execute putChar of 1. Okay. Here your a is 2. So you have to again call the function f of x and putChar as 2. Then you again call the function with a equal to 3, f of x. Then you do putChar of 3. Then you again call with a equal to 4. You do putChar of 4. We call f of x with a is the null new line character. If x is the new line character, your if condition becomes false. Then again your if condition becomes false, so you exit from the function. Right? So you exit here. Now to calculate the output, you calculate the yield of the tree. So you trace from here. Now there is a putChar of 4, so 4 is printed. PutChar of 3, 3 is printed. PutChar of 2, 2 is printed. PutChar of 1, 1 is printed. And so this program will terminate with output as 4, 3, 2, 1. Okay. Fine. Any questions before I end the class? No? Feel free to ask any questions if you have. I will not take much time of yours. It's a critical time. like 1 month is left. So prepare well. Hope this class was helpful. You get to learn the various aspects of unsupervised learning. We will learn hierarchical clustering and solve some more questions in the next class. So thank you for joining. See you guys day after tomorrow in the next class.